So we are recording, and we're looking at systems of linear equations. That's the unit we're in, and we're doing a quick overview of where this learning sits. I added a little link there. I'm not going to take you through it, but if you're interested, you can click on that. It says careers that use linear equations, like we're studying right now, and there's a whack of them. Anything that has kind of sciencey or mathy stuff involved in it, like computer programming is a really obvious one, but any careers that have sciencey and mathy stuff going on, systems of linear equations are a very common thing. It's something that a lot of our technology is built upon the math involved in that. Okay, so in grade 9, you were really focused on linear equations, right? So you were focused on linear equations. Usually you would have been doing them in the slope y-intercept form. So like y equals 3/4 x minus 4. You know, you might have something like that, and you'd have to graph it, and you'd have to figure out stuff about it. So that was grade 9. But in grade 10, we focus instead on just a single linear equation. We focus on systems of linear equations. So we're looking at groups of them. And specifically in 10th grade, you're looking at 2 linear equations and how they work together. So 2 linear equations at a time, right? So we've gone from 1 linear equation at a time in grade 9 to 2 linear equations at a time in grade 10. Now, could you end up doing more than that? Yeah, you could. You could have 3 linear equations. You could have 4. If I were to talk about the 2 we'd have, we might have one that looks like y equals 2x plus 5, and then we might have another one that's in our standard form, 3x minus 2y equals 16. So now in 10th grade, you need to deal with these 2 at the same time and figure out stuff about them. Okay, so that's the big difference between 9th grade and 10th grade in terms of our linear algebra. So there are a couple of forms of linear equations, right? We've got our first one is our slope-intercept form. And what do we do when we got our slope-intercept form? Well, if we want to graph it, we are going to first look for the y-intercept, and then we're going to follow the slope from there. So I might have an equation, again, where my previous one was y equals 3/4 x minus 4, right? So I would say, okay, my y-intercept is right here. So I'm going to graph the point minus 4 on my y-axis. So that would be 0, -4 as my point. And then I'm going to follow the slope, which tells me rise 3, run 4. So up 3/4, up 3/4, up 3/4. So that's how I do my graphing if the equation is in slope y-intercept form, where we get the y on one side and everything else on the other side. The other type we might have is it's in standard form. So standard form is just a different way of writing equations. I'm just going to pick one here. I might have 2x plus 3y equals 9. That's my standard form. And if I wanted to graph something when it's in standard form, I'm going to find the y and the x-intercept. But you can't just look at the equation and know them as easily as you could get the y-intercept in the previous one. So to find the y-intercept, I'm going to sub in x equals 0. So to find the y-intercept, I'm going to put a 0 in for x, and then I'm going to solve for y. To find the x-intercept, I'm going to sub in a 0 for y and then solve for x. And then I would graph those 2 intercepts. I would put the points on my graph and I'd draw a line through them. So that's my standard form, and those are the 2 different ways we would do graphing with our slope-intercept form and our standard form. Now, we're talking about solving, right? So to solve, if you've got one equation, you need to have just one unknown. So what would that look like? If I were to write that, I might write like 3x minus 8 equals 2x plus 4. So this is an equation. It's only one equation, and it's only got one unknown. It happens to show up in 2 places, but it's only got x's in it. X is the only unknown. So I could solve for this. I could solve for x because it's one equation and it's got one unknown. But if I have 2 unknowns, say an x and a y, that means I need 2 equations to solve it. So in order to solve for two unknowns, I would need two equations. Let's say we had one that was 3x plus 2y equals 12. And let's say I had y equals 4x minus 6. I've got two unknowns, x and y, and I've got two equations. So I can solve. I can solve for this. If I only had one equation, I would not be able to solve. If I got two unknowns, I need two equations. Well, that means it's also true for n, right? N could be any number. And this is a notation, meaning you start at 1 and you keep going up. If I have any number of unknowns, say 12 unknowns, that would mean I would need 12 equations in order to solve for those 12 unknowns. If I had 100 unknowns, I would need 100 equations to solve for those 100 unknowns. So the numbers match, which kind of makes it easy to remember. You will do stuff in grade 12 math where you'll be solving for bigger systems of equations where you might have an equation with an x, a y, and a z variable, 3 variables, and so you would need 3 equations to solve for those 3 variables. That's pretty tricky, and we're not doing that in this course. That's something for later. All right, so the next question would be, well, what does solve really mean? When you see a problem and it says solve, like what does that even mean? Well, solving means finding the point of intersection. So we've got two lines. We got to find where they touch each other. Where do they touch? Where's our point of intersection, our POI, point of intersection, right? So it's going to be written as an x and y pair, an ordered pair. So an example might be 4, -3, meaning your point of intersection is at an x coordinate of 4, a y coordinate of -3. So we're talking when we say solve, we mean find the point of intersection, write it down as an ordered pair, meaning a point on a graph. So it's usually an important point, the point of intersection. That's why we want to solve for it, because it usually tells us some very important information about something. So I'm going to give you an example. It's maybe a little bit of a goofy one, but it's kind of how linear equations could be used. Here's an example of you versus a horse in a running race. Now you might say, horse is faster, horse is going to win the race for sure. But that's not entirely true, because to get a horse to go in the direction you want it to, you're usually going to need a rider. You're going to need a rider. If you haven't trained the horse specifically to go to a specific point, you're going to need a rider. And for the rider to ride the horse, they probably want to be comfortable, so they're going to need a saddle. So they're going to need to actually put the saddle on the horse. So when that starting gun goes in the race, you take off, and the person with the horse needs to fiddle with the saddle and get the saddle on the horse, and then they need to start chasing you. Now the horse is faster, so at some point, if the race is long enough, the horse will catch you. But if the race is short enough, you'll win. So in a race like that, we could actually represent that using linear equations. So it's a race. You can run 0.2 kilometers, that's 200 meters every minute. The horse can run half a kilometer, that's 500 meters every minute, but it takes 6 minutes to saddle the horse. How far can you get before the horse catches you? So I'm not going to take you through the system of equations, and we're not going to solve all the systems of equations. What I do want to point out is our point of intersection is important. So here's our graph, right? You are the blue line. Your distance is 0.2 kilometers times t for the number of minutes. And that graph makes a blue line. You start at 0, 0, and you just keep going along, but it's not a very steep line. The horse doesn't start until 6 minutes have already passed on our graph, but it's a steeper line, so it's going to cover that ground faster. So on that brown line, we can see the horse's distance. And that point of intersection is where the horse catches you, where something catches up to something else. Okay? So I think you can imagine probably why things like traffic lights would be based on systems of linear equations, right? Because if we have things starting and stopping and moving different speeds. So, you know, this is kind of a silly example, but it shows why the point of intersection is important. It's usually a very meaningful point in what we're doing. So that's what we mean when we say solve. We find that point of intersection. Now, there's a couple ways to do it, right? And we'll talk about those in a moment. We could really have 3 different situations here. when we're looking for the solution of a system of equations. The first one's the most common one. That's where there's one solution. So let me get my lovely highlighter here. So that's right here, right? That's where the 2 points cross. We've got one solution. And we'd write that as an ordered pair. So one solution, they intersect at one point. Now these words consistent, independent, you don't need to know those. Those are just ways of describing this relationship, but you don't have to worry about memorizing those or anything. We're not going to worry about those. The second possibility is that you've got no solution, and that means the lines are parallel. So when you would try and solve, you'd end up with a problem in the math. You might get one number equaling another number, like 0 equals 9, and you'd say 0 doesn't equal 9. That would mean that there's no solution. So when you're trying to solve for these, if you do it in graphical form, you'll see that their slopes are the same, but their intercepts are different, and they're parallel to one another. But if you're trying to do it with the algebra, you'll notice that there's a problem. Our last possibility is that the two lines are equivalent lines. And they're equivalent, meaning they're the same, but they just look, the way their algebra is written, they look a little different. And they would have infinite solutions, meaning they're on top of one another. I actually want to take you for a moment to a program called Desmos. Can you let me know in the chat if you've used Desmos before, please? So go ahead and post in the chat right now. Let me know if Desmos is a program that you've used in school. I imagine some of you have. Okay, I'm getting a bunch of yeses. Desmos, so Wadi, Devin, Matthew, Olivia, Jacob, Serena. Okay, I'm seeing everybody saying yes, you've used Desmos before. Luca, you haven't. That's okay. But a lot of you have, so this might look a little familiar. In Desmos, I can just type in an equation, right? So I'm going to type in x, a nice simple one, x plus y equals 2. So there is my line. Okay, so Desmos did the graphing for me. It graphed that line for me. X plus y equals 2. You'll notice that my x and y intercepts are both 2, because if I put in a 0 for y, x equals 2, and if I put in a 0 for x, y equals 2. So my intercepts are 2 and 2, so that's my line. I'm going to make an equivalent line. So here I go. I'm going to make an equivalent line. My new line is going to be 2x plus 2y equals 4. Now you notice my green line is overlapped by a purple line. These two lines are identical. Even though they look different, their equations look different, they're the same. Okay? I'm going to write one more, a new expression that's going to be an equivalent line, meaning there's infinite solutions. 5x plus 5y equals 10. Now I've got a new black line that is on top of those. In the chat right now, I would like you to write me a new, meaning it's different from any of those three, a new equivalent line equation that would be a line that would overlap all of the lines, the three lines that I've drawn so far. So I'd like you in the chat right now to write me down an equivalent equation of a line. It'll graph exactly the same, but it'll look a little different, just as all my three do. I'm going to pause the video, go for it right now, and post that in the chat, please. Okay, so those are three situations that we can have for solutions of systems of linear equations. One solution, no solutions, or infinite solutions, right? So things we're looking for there are things like, are the equations the same, are they equivalent? Are the slopes the same but the y-intercepts are different? Or do they have different slopes? Okay, now methods for solving. I'm not actually going to do examples here. I'm just going to talk about the methods we're following. So first method would be graphing. You got two equations, you graph them, you look on the graph and see where they intersect. And that's your point of intersection, that's your solution. Next one is substitution. And of course, our third one is elimination. Those are our three techniques. Let's have a look at substitution and elimination specifically. For substitution, I'm going to isolate one variable in one equation. Sometimes it'll already be ready to go. You may have one that's already ready to go. An example of what that would have to look like in the end would be you'd have to have, for example, x equals 3y minus 2. In this example, my x is isolated, it's ready to go. I'm ready to take what it's equal to, 3y minus 2, and substitute that into my other equation anywhere I see an x. So I've got to isolate one variable in one of the equations. Maybe it's already comes isolated and I don't have to do anything. Then I'm going to sub it into the other equation. I'm going to solve for my first variable. And I'm going to sub back into one of the original equations to find my second variable. So if I subbed in for x, my second equation would now only have y's. I would figure out what y is, and then I would sub that back into the original equation to get x. So substitution, you got to sub one equation into the other. Our other type is elimination. That one's a little bit trickier, I think, but it's much faster for certain examples. So with elimination, you're going to multiply one or both equations to make an equivalent equation, just like we did in the chat, where the coefficient is the same number for x or y. Do you have a question, Wyatt? Go ahead. Yeah, I'm actually going to post the video and this PDF as soon as I'm done, so you'll have access to them there if you're writing them down, okay? So I want to do this kind of quick, but as soon as I'm done, while you're working on your other stuff, I'll post them. My second thing I'm going to do after I make an equivalent expression, so I got the coefficient, the number in front of the x's, or the y's being the same, I'm going to add or subtract the second equation from the first. So I could add if the numbers, the coefficients, one was positive and one was negative. When I add them together, they'd equal 0. Or I could subtract if they're both positive, or subtract if they're both negative. And then they would cancel out. And I'll solve for the first variable. And then I'm going to sub back into the original equation to find the second variable. So this was a really quick tour of the key ideas from this unit. Okay, so I hope this will help you just to give you a good overview of what this unit looks like.